Hello students, how are you all? I sincerely hope that you all must be keeping high spirits, right? So let's start with today's session. Today we will be discussing the types of variables and constants. Basically, it can be broadly classified into four types, right? So one is dimensional constant, dimensional variables. Then there are dimensionless variables, dimensionless constants. So these are the four different categories in which the various variables and constants can be categorized. We will discuss each one of them in detail along with some examples, right? So first is dimensional variables. Now look, from the term, it is absolutely clear that I am talking about those physical quantities which possess both dimensions as well as whose values are not fixed. That is, they vary, they can change. So dimensional variables are those physical quantities having dimensions and whose values are not fixed. Now we can come across various physical quantities which satisfy this condition, like force, mass, momentum, impulse, pressure, and so on. These all are the physical quantities which have got dimensions. SI unit of force is Newton, mass is kg, momentum is kg meter per second. So all these quantities possess dimensions, that is, they can express in the powers of the fundamental units of mass, length and time, right? And these values are not constant. Obviously, mass of different bodies is different. Different forces can be applied on various bodies. Momentum of bodies moving with different velocity or having different mass are also different. So these are the physical quantities which we are talking about are having both dimensions but their values are not fixed. So they come under the category of dimensional variables, right? Second category is dimensional constants. Look, again, it's pretty clear from this, dimensional constants. So these are those physical quantities which possess dimensions as well as they have fixed value. Fixed means constant value. Their value is constant throughout, it can't change. So those physical quantities which have some dimensions and also whose value doesn't change, its value remain fixed, comes under the category of dimensional constants. Let's take some examples. Gravitational constant, you are aware of it, right? Gravitational constant, it is actually the universal gravitational constant. So its value remains fixed throughout the universe, but it has got some dimensions, right? Similarly, solar constant, it is represented by S, solar constant. Yesterday only we discussed, it is the amount of energy received by a body placed on the Earth's surface from the Sun per second per unit area. So its value is also fixed. Its value do not change. And obviously it has got some dimensions, watt per meter square. So there are some other examples as well. H, it stands for Planck's constant. It is Planck's constant, right? So this has also got some constant value. And also it has got some dimensions. Its SI unit is joule second. So it has got dimensions. So these are the physical quantities which are having dimensions but their values are fixed. So they come under the category of dimensional constants, right? Third category, dimensionless variables. Okay, again, from the heading it's itself clear that we are dealing with those physical quantities which do not possess any dimensions and their values are also not fixed. So those physical quantities which neither possess dimensions nor possess a fixed value are known as dimensionless variables. Right? So students, examples of dimensional variables are like dimensionless variables like angle. Right? Angle. It is length of the arc divided by radius, ratio of two similar physical quantities. So it is a dimensionless quantity, but it does not have a fixed value, isn't it? Its value can vary. So it is a dimensionless variable. It do not have a fixed value. Understood? Okay. Similarly, second is you can consider the case of strain. Strain actually is, we'll discuss it in the subsequent session, it is actually change in dimension of the body divided by original dimensions. That is, in one dimension you can consider change in length divided by original length, or change in volume divided by original volume. So it is again the ratio of two similar physical quantities. So obviously it would be a dimensionless quantity and its value is also not fixed. Therefore it comes under the category of dimensionless variable. Right? Then there comes specific gravity or relative density, which is again the ratio of two similar physical quantities. Density of the substance divided by density of water at 4 degrees Celsius. So, being the ratio of two similar physical quantities, it is a dimensionless quantity. Again, its value for different substances different. So, these are the quantities which possess no dimensions and their values are also not fixed. So, they come under the category of dimensionless variables. Right? Last category. Dimensionless constants. So again, these are the physical quantities which do not possess any dimensions, but they have fixed values. Not having any dimensions, but having fixed value. There are various examples of this. All the pure numbers, 1, 2, 3, 4, 5, 6 and so on. They are dimensionless and they are constant. The value of pi, that is 3.14, it's a constant, isn't it? Having no dimensions, right? Then the value of e, exponential, 2.718, it's a constant, having no dimensions. Clear? So, dimensionless constants are those quantities having no dimensions but having fixed value. All the pure numbers will come under this category. Then the value of pi, e, exponential, they are the examples of dimensionless constants. So students, these are the 4 different categories in which various variables and constants can be grouped or can be divided. Right? Now, before proceeding further, we are presently studying the topic of dimensional analysis. In the previous lecture, we have understood the meaning of dimensions, right? We have found the dimensional formula for various physical quantities. Now we have classified the variables and constants into these 4 categories. Now we will discuss the uses of dimensional analysis, and then obviously there are some drawbacks of dimensional analysis as well, which also needs to be studied. But before that, we need to discuss the principle of homogeneity of dimensions. So that's an important one. We are going to discuss principle of homogeneity of dimensions. Principle of homogeneity of dimensions. Now look, it's based on a basic fundamental thing, right? Whenever a physical relationship between various physical quantities is given, whenever a formula is given, then the dimensions of all the terms on either side of the relation must be same. It is only then the formula or the given relationship can be considered to be dimensionally correct. Right? So, what I mean to say is that for a given physical relationship between different physical quantities to be dimensionally consistent, the dimensions of each and every term on either side of the equation must be same. And that is the principle of homogeneity of dimensions. Right? For example, there is a formula, suppose A plus B is equal to C plus B plus E. Let us assume A, B, C, D, E. Let us say these are different physical quantities. So, if this formula is to be dimensionally correct, then the dimensions of each of these terms on either side of the equation, that is on left hand side as well as on right hand side, each term on either side of the equation must have the same dimensions. Suppose physical quantity A has dimension of kg, then it is mandatory that all the other terms on both sides must also have the same dimensions of kg. This is known as principle of homogeneity of dimensions. It's based on a very simple concept, isn't it? It is based on the fact, on a very simple fact, that two similar physical quantities can be only added and subtracted. Two similar physical quantities. You cannot add mass with length, isn't it? It will be totally absurd. Can you add this 10 kg plus 2 meter? Can you add this? You can't do this because it is dimensionally incorrect. Only similar physical quantities can be added or subtracted. In case it is 10 kg plus 2 kg. These are the two quantities we are talking about are similar. They represent mass. So they can be obviously added up. So in simple language, it is only when the physical quantities are similar that they can be added or subtracted. Right? So, principle of homogeneity of dimensions states that for a formula to be dimensionally correct, the dimensions of each and every term on either side of the equation must be same. That is the principle of homogeneity of dimensions. I'll give you some other example as well. Suppose we are all aware of equations of motion, isn't it? We all are aware of equations of motion. So, first equation of motion, second equation of motion, third equation of motion. We have done it in class 9th. So, what is the first equation of motion? It is V is equal to U plus AT. This is the first equation of motion. Right? Let's see whether it is dimensionally valid or not. This is velocity. What is the unit of velocity? Meter per second, having dimensions of LT minus 1. This term. U represents velocity. This is also velocity, having dimensions of LT minus 1. Let's see this term, this entire term, A multiplied by T. Acceleration, its unit is meter per second square. Time, its unit is second. So we get meter per second. So it is LT minus 1. So look, this formula is dimensionally correct because all the terms on either side of the equation possess the same dimensions of LT to the power minus 1. So it is dimensionally correct. So similarly, there are certain numericals in which by using the principle of homogeneity of dimensions, we can easily find out the dimensions of some unknown physical quantity as well. Right? So this is the concept of principle of homogeneity of dimensions. You can consider other examples as well. Like second equation is S is equal to ut plus half at square. This is the second equation of motion, which is also known as displacement time relationship. Right? It is known as displacement time relationship. Now left hand side, this is the displacement. SI unit is meter. So dimensional formula is L, isn't it? Now what about this? This is velocity, meter per second, and this is time second. Second per second cancel, we will be left with meter. So this term, it has got the dimensions of L. Let's consider this third term. Half, it's constant, having no dimensions. Acceleration, it's meter per second square. Multiplied by time square, it is second square. So we are left with meter. So its dimension is L. Look, each term on either side of this equation possesses the same dimensions of L. That is, this formula is dimensionally correct. So once again I repeat, principle of homogeneity of dimensions states that for a physical relationship between different physical quantities to be dimensionally correct, the dimensions of each and every term on either side of the equation must be same. That's the mandatory condition, right? And also what we have discussed is the two similar physical quantities can be only added or subtracted. Dissimilar physical quantities can't be added or subtracted. It's a common sense, right? Only when the physical quantities are similar, then only they can be added or subtracted, right? Okay. After doing this topic of principle of homogeneity of dimensions, let's see the various uses of dimensional analysis. Okay, first use. Let's first theoretically discuss each and every use of dimensional analysis, and then we will discuss each use in detail along with some numericals based on those topics, right? First use is dimensional analysis can be used to check the correctness of the formula. It can be used to check the correctness of the formula or of the given physical relationship between different physical quantities. So this is the first thing. It obviously is based on the principle of homogeneity of dimensions. The first use is it can be used to check the correctness of the given physical relationship between different physical quantities. Second use. Suppose a physical phenomena is taking place in which some physical quantities may be involved. In such a scenario, dimensional analysis can be used to obtain a relationship between those physical quantities involved in that phenomena. Right? We will discuss various numericals based on the second usage. So second use is to derive relationship between different physical quantities involved in a phenomenon. So the second use is to derive relationship between different physical quantities involved in a physical phenomena. This is the second use. We'll discuss a lot of numericals based on this, right? Third one. Now I've told you one of the major advantages of SI is that SI system can be easily converted into another system. So with the use of dimensional analysis also, one system can be easily converted into another system. So using dimensional analysis, one system can be converted into another system. So conversion of one system into another. So these are the three uses of dimensional analysis, right? So I repeat, first use is to check the correctness of the formula. In this session, we will discuss this use, right? Second is to derive the relationship between different physical quantities involved in a physical phenomena. We will discuss these 2 points in the subsequent lecture. Third is dimensional analysis can be used to convert from one system into another system, right? So what we do is, let's start with this particular topic to check the correctness of a given physical relationship between different physical quantities, right? So let's consider the first numerical. Suppose we are required to check the correctness of the given formula, right? This is the formula, suppose H equals to 2t cos theta divided by r rho g. This is basically an ascent formula. Look, when capillary tube is a glass tube open at its both ends and it's having a narrow bore. When it is immersed in a liquid, then what happens is liquid either rises or falls in the capillary tube. So this is basically the height through which the liquid rises or it falls. So this is known as ascent formula, right? So we are supposed to check the correctness of this formula. H equals to 2t cos theta over r rho g. H is the height, T is the surface tension. T is the surface tension. There's an entire chapter dedicated to this topic, surface tension. So definitely we'll be discussing this topic in detail. For now, just remember the formula. Surface tension is force per unit length, right? In order to check the correctness of the formula, you need to know the dimensions of each and every physical quantity. Then only you can solve such numericals. Okay, rho is the density. G, as you are aware, is the acceleration due to gravity. So how to check whether it is dimensionally correct or not? What to do is consider left hand side. What is the dimensions of left hand side? It's height, so it is meter, right? Consider right hand side. Twice, it has got no dimensions. It is a dimensionless constant. It is a dimensionless constant. This two, all the pure numbers are dimensionless constant. Cos theta, it's a trigonometric function, right? Base over hypotenuse, ratio of two similar thing. So obviously, it is also dimensionless quantity, having no dimension. So you need to avoid it. They are having no dimension at all. Tension, it's force per unit length. Look, force per unit length is, force is kg meter per second square divided by length is meter. So it is kg per second square. So tension, its unit is kg per second square. Radius, it is meter. Density, mass over volume, so it is kg per meter cube. Acceleration due to gravity, it's acceleration, that is meter per second square. Let's check it out. Per second square get cancelled. Kg get cancelled, right? Meter into meter, meter square, so it will be left with m minus 1, so which will be equal to m. Now look, left hand side and right hand side both has the unit of meter. That is, both has the dimensions of L. Left hand side and right hand side both have got the dimensions of length. Therefore, this formula is dimensionally correct. Therefore, this formula is dimensionally correct. Now student, I must mention here a very, very important thing. A dimensionally correct formula need not to be a correct formula. What I mean to say is that here cos theta, even if I replace it by tan theta, then only this will be dimensionally correct. But the formula is not correct, right? Otherwise the formula is not correct. So for a formula to be correct, only the equality of the dimensions on both sides of the equation is a necessary but not sufficient condition for the relationship to be valid, right? So tan theta is not correct, so it will be actually cos theta. So this is one of the drawback of dimensional analysis. Even if I replace this 2 by 3, 4, 10, then also it will remain dimensionally correct. But it is not the actual formula. Actual formula is 2t cos theta. This is, students, one of the major drawback of dimensional analysis. That is, the equality of dimensions on the two sides of an equation is a necessary but not sufficient condition for the validity of the relationship. Right? Do mark my words. It's an important constant. So dimensionally this formula is correct. Let's discuss some other question as well based on the checking of the correctness of given formulas. Right? So what to do is, let's consider some other example. Suppose we need to prove that nu is equal to 1 by 2L square root of T by n, or rather F by n, this is force, suppose. We need to check whether this formula is dimensionally correct or not, right? So what to do? This is frequency, for instance, this is frequency, this is length, this is force, and this is mass. This is suppose mass, right? So let's see, m is given to be mass, f is given to be force, L is length, and nu is suppose frequency. So left hand side, frequency, you are aware, it's the reciprocal of time period, so its unit is per second, right? Dimensional formula would be t to the power minus 1. Per second is also known as hertz. Now consider right hand side. Okay, 1 by 2, it's a dimensionless constant. Square root of F, force, it is kg meter per second square. Mass, it is kg. And length, it is meter. It's okay? So, kg get cancelled. So what do we get? Square root of 1 by m s to the power minus 2. So we get s minus 1, right? And over here, what we get is m square root means half minus 1. So it is s minus 1 m to the power minus half. Now look, the dimension of left hand side is t to the power minus 1, while the dimension of right hand side is n to the power minus half t to the power minus 1. So since the dimensions of left hand side is not equal to the dimension of right hand side, therefore this is an incorrect formula. So this is an incorrect formula, right? Now how to correct it? How to correct it? Suppose m is not mass, m is given to the mass per unit length. Suppose small m is not mass, it is mass per unit length. Let's say in this case, what will happen? So in such a case, let's see whether now the formula is valid or not. Okay, right hand side, 1 by L it's meter, force it's kg meter per second square. M is not mass, now I have considered m to be mass per unit length. So it is kg per meter. Right students? So kg get cancelled, what do we get? Meter square per second square divided by meter. So it will be meter per second divided by meter. Meter get cancelled, will be left with per second. So now this formula is dimensionally correct. When m is considered to be the mass per unit length, that is small m is mass divided by length, then the formula becomes dimensionally correct. So these are some of the uses of dimensional analysis. So any given formula, we can check whether that given relationship is dimensionally correct or not. So students, we will wind up this lecture, and in next session we will discuss some more numericals. Also we are supposed to discuss the other two uses of dimensional analysis, right? Till then, do take very good care of yourself. We will continue in the next session.